Let's practice calculating the standard electromotive force, which is the voltage of a reaction. So this is sample exercise 20.6. Using the standard reduction potentials listed in table 20.1, I believe this is 20.1 here. Okay, it says find the voltage. Okay, so we're gonna look at this Cr207. I'm going to look at the charge so I know which one's being oxidized, which one's being reduced. So oxygen here has -2 each, -2, and there's 7 of them, so total of -14 here. And so this has to be a total of +12. So +12 minus 14 is -2, which means the oxidation state of chromium is +6, and the oxidation state of oxygen is -2. Okay, so I'm going to look over here to chromium. Chromium's oxidation state is +3. So it looks like Cr got reduced. So I'm going to write that down. So chromium, Cr207 -2, arrow, 2 Cr +3. Okay, so what I'm going to do next is just balance the atoms here. You have 2 chromiums. Next, I'm going to balance the oxygens. You have 7 oxygens, so I'm going to add 7 waters on this side, which is this right here. So I've used this and this. And now to balance the H's, I'm going to add 14 H pluses. Okay, which is the same as this. Okay, so everything's balanced. Now I just have to balance the charge by adding electrons. Here I have 14 pluses, -2, +6. So here I have +12 and +6. I'm going to add electrons to the more positive side. So it would be here. And how many electrons did you add? That's correct. I would add 6 electrons. So when you add 6 electrons plus 12, you're going to get +6. Okay. So it looks like this chromium used to be +6, now it's +3, it got reduced. So this is the reduction half reaction. And another way I can tell it's a reduction is because you're adding 6 electrons to it. So it's becoming more negative on the right side, so it got reduced. Okay, so the other half reaction must be the 6I minus becoming 3I2. So the charge here is 0, the charge here is -6. So I'm going to add 6 electrons to the more positive side. So now it's 6 minus, 6 minus, it's equal. Okay. So it looks like I minus got oxidized. So this is the oxidation half reaction. The next thing I'm going to do to get the voltage of the cell is to look up in the chart the potential for the reduction of Cr207, which is given here. So it's the reduction. This is a reduction chart. So all the reactions are written in a reduction format. So it's the reduction of this is positive 1.33 voltage. Okay. So I'm going to do my formula. E cell is equal to E cats are better than ants minus E anode. The reduction is the cathode. Reduction is what happens in the cathode, and oxidation happens at the anode. So the cathode is, what was it again? It was 1.33. This is the cathode, so the voltage is 1.33 volts minus the anode is I2 and I minus. So I is given here, and it's written backwards. I2 reduced to I minus, but in the equation above, it's being oxidized. So I'm going to take positive 0.54, put positive 0.54 volts, and the negative sign here from the formula will reverse that reaction. So you do that math. The answer is 0.79 volts. So this is the electrochemical cell potential when you mix these together. Okay, let's try another one. It says the voltaic cell is based on the following two standard half reactions. Notice they're both written as reductions. Okay, so now you're going to use Appendix E, and you're going to determine the half reaction that occurs at the cathode and the anode. Remember, cathode is where reduction takes place, and anode is where oxidation takes place. A and O are both vowels, C and R are both consonants. Okay, then you're going to determine the standard cell potential, which is E cell. Using that formula, E cathode minus E anode. Okay, so first I have to decide which one will be reduction, which one will be oxidation. The Appendix E in your textbook, if you can look that up, looks like this. And this is also linked in your calendar so you can see it. So here's the reduction of cadmium plus 2 to become cadmium solid, and this is the reduction of the tin. Okay, so one of them will become the anode, one of them will be the cathode. So noticing the numbers, who wants the electron more, Sn plus 2 or Cd plus 2? Okay, so this is negative 0.403, so it doesn't want the electron at all. But the Sn plus 2 doesn't want the electron either, right? But this one is a lower negative number. So I'm going to use this as the reduction. And what I will do is I will use cadmium, go backwards, and give away the electron, which will make this, put a negative in front of it. So this will become positive, which will give me a positive cell potential. And that's how I decide which one will be the anode, which one will be the cathode. So I'm going to use tin plus 2 as the reduction half reaction. Okay, so I'm going to write it just the way I see it. So there it is. I'm going to write it like this. Sn plus 2 electrons is Sn. Okay, so here this is going to be Sn plus 2 got reduced. So this is the reduction. And the reduction happens at the cathode. So this is the cathode. Okay, which means I'm going to have to reverse this reaction. Okay, so it'll be Cd arrow is going to have to give away the electrons for tin to get it. 2 electrons plus Cd plus 2. Okay, as you can see, cadmium got oxidized, and this is what happens at the anode. And you just answered letter A. Now for the standard cell potential, I'm going to go ahead and go E cell is equal to E cat minus E anode. I'm going to look up the cathode half reaction, which is tin. Look it up at Appendix E, and that is negative 0.136. Negative 0.136 voltage. Okay, then I'm going to look at this potential for this half reaction, the cadmium, and it's being oxidized, so I have to flip it, the reaction. So cadmium is written here, written as a reduction. So it's normally negative 0.403, but if you flip it, you're going to put a negative in front of it in the formula. So negative 0.403. This negative will cause this negative 0.403 to become positive, which will make my reaction have a positive voltage, which is going to be 0.26 volts. Because this is positive, then it is spontaneous because you're able to get some potential, some energy out of that. So electrons move across. Okay, so that's how you do it. Okay, so when they give you two reactions, find the one that is going to be the reduction and the oxidation, and then plug in the voltage in the formula. Okay, so this is the table. The reduction table, I think, is 20.1. And as you can see, this is positive, which means F2 really wants electrons. Okay, and if you go down here, this is negative. So Li plus really hates electrons. So if you try to force it, if you try to reduce it, you have to put in energy instead of it giving away energy. Okay, so that's what the negative potential means. Li plus hates electrons, or it does not want to be reduced, or lithium plus does not want to be reduced. That's what the table means. Okay, so the best oxidizing agent is the electron stealer. Electron stealer, oxidizer. Who wants to steal electrons? It would be F2 because it wants to be reduced. Positive, you get a voltage of positive 2.87 volts when it steals electrons. Okay, the best reducing agent, a reducing agent wants to give away electrons. That means it hates electrons. Okay, so that would have to be LIS. It wants to go backwards. So Li solid wants to give away electrons. If it goes backwards, this becomes a negative in front of it, positive 3.05 cell potential. The most active metal is the metal that wants to give away electrons. That would be, what do you think? You're right, that would be lithium. It's even more active than sodium, right? Okay. So now let's do another example. It says rank the following ions in order of increasing strength as oxidizing agents. Okay, let's think about this. Oxidizing agents are electron stealers, right? They want electrons. Okay, so what would that be? Would that be on the top of the chart or on the bottom of the chart? You're right, it would be on the top. It wants electrons up here, giving you a positive potential. So, increasing strength as oxidizing agent, that would be this side wants electrons, right? And then this side hates electrons. Okay, go ahead and pause the video and try to answer that question. Who wants the electron more, nitrate, silver ion, or chromate, dichromate? It would be, this is on top, so positive 1.33. It would be Cr2O7 minus wants the electron. And next one would be NO3 minus, then Ag plus. So out of this list, Ag plus hates the electrons. It only gets the potential of 0.80 while the other ones get 0.96 and 1.33 voltage. Okay. Using the table, rank the following species from the strongest to weakest reducing agent. Pause the video and try this yourself. Okay, reducing agent. That means it wants to reduce something, so it wants to give away electrons. So that means it hates electrons. Okay, so then you would pick, so from strongest to weakest. So this would be, if you were to chart it, strongest to weakest, strong reducing agent hates electrons the most. And over here, I would go this way. This one is the strongest, hates the electrons the most, and this one would not hate electron as much. Okay, so who would hate the electron? I minus FeAl. So lithium hates it the most, so I would pick Al, then Fes, then I minus. So Al would give away 3 electrons, then Fe, then I minus. Okay, if this one gives away the electrons, you will gain a potential of negative 1.66. If iron gives away the electron, you will get a potential of negative 0.44, which is positive 0.44. Okay?